going to start the NumPy section now.
Single integer within lists using built-in int type, it requires a lot more space than NumPy. So basically the takeaway from this is that because NumPy uses less bytes of memory, the computer can read less bytes of memory quicker, obviously, so it's faster in that regard. Another reason I didn't specifically say is that when we're iterating through each item in a NumPy array, we don't have to do type checking each time. So in Python built-in lists, you can have a list of like an integer, then a float, then a string, then a Boolean, and you have to check each element you're looking at what type it is, but NumPy we don't have to do that. So another reason it's faster is that there's no type checking when iterating through objects. Moving on, another reason that NumPy is faster than lists is because NumPy utilizes contiguous memory. So what that means is imagine that this kind of array-like structure is our computer's memory. So we could store information in any one of these memory blocks. So if we had a list, the way that would look in a list's memory is that our list would be kind of scattered around. So maybe we have a list that takes up 8 memory blocks. The thing is that these memory blocks aren't necessarily next to each other. So you have some information here, you have some information here, you have a good amount of information in here, then you skip a block here, and skip 2 blocks, you have some information here. So it's all kind of scattered around. So kind of, if you have an 8-item array, what that looks like is that that array is actually just, or that list is just containing pointers to the actual information that's scattered around our computer's memory. And so it's just that all the information is not right next to each other. Kind of you have to bounce around your computer's memory a bit, and it's not super fast to like rapidly go through and kind of potentially perform functions on all items at a time or subsets of the items. NumPy array, however, uses contiguous memory, so all 8 blocks in this case would be right next to each other, and this has all sorts of advantages. And also just to mention real quick, you'd also like, kind of have to store somehow where the start of that memory is, and then like the total size and the type of memory block. But it's a lot easier than this kind of pointer structure that's up here. And so the benefits of NumPy using this contiguous memory are a couple different things. So the first benefit is that our CPUs, or our computers, have these SIMD vector processing units. And so when this memory is all like right next to each other, we can utilize this unit. And basically what SIMD stands for is single instruction, multiple data. So we can, like, if we have to do an addition of like a lot of values, instead of just doing one addition at a time, we can use the SIMD vector unit and basically perform computations on all of these values at one time. So it's quicker in that regard. Another reason it's quicker is that we more effectively utilize our cache, so our kind of our quicker memory in our computer. Basically, if we load in all these values, we can keep them close to where we need to access them, and like perform all sorts of operations. While as in the list case, you maybe load in like half of this, but then this other half, because it's scattered around in different places, you'd have to like go back and like reload that in to your cache, like, you know, just be overall slower because you have to do more like longer memory lookups within your computer. Okay, so we've kind of went over some of the performance benefits, but how are lists different from NumPy? Well, lists we can do insertion, deletion, appending, concatenation, etc., and we can also do the same exact things in NumPy. I guess the big difference though is that within NumPy we can do all that, and we can do lots more, and we'll see the lots more throughout the video. But as a simple example, imagine we have these 2 arrays. One thing that we can do that's really nice in NumPy is that if we try to multiply these one item at a time, we could do that in lists. You couldn't multiply 1 and 1, 3 and 2, 5 and 3, etc. But when we do the exact same computation within NumPy, it allows us to do these, you know, single value, like item-wise computations, which is pretty neat and pretty useful. So that's one example, and you'll see a lot more throughout the video. So applications in NumPy. There's all sorts of applications. I think the first one that comes to my mind is that is a kind of a MATLAB replacement. You can do all sorts of mathematics with NumPy. And I think I should say that I think the SciPy library has even more mathematics like functions and whatnot. So if NumPy isn't cutting it for you, try to look through the SciPy documentation. You might be able to find even more. But yeah, it's pretty powerful, the math that NumPy can do. It's useful in plotting. It is the back end of many different applications. So pandas, which I've done a video on before, it is just like the core component of pandas library. It really allows pandas to work. If you've seen my Connect 4 how to program that video, I use NumPy to store the board. And then in future videos I'm going to do, you can actually store images through NumPy, so like PNG images. You can use NumPy to store all the information and like do all sorts of cool stuff that I'll post future videos on. Let's see. Also, another, I think, useful reason to know NumPy is that it's kind of like pretty important for machine learning applications, both directly and then also kind of indirectly, because one of the key libraries or key kind of concepts you learn with machine learning is the idea of like tensors. And tensors are pretty connected to kind of like, the tensor libraries are pretty similar to like the NumPy library. It's just a way to store all sorts of values. So knowing NumPy will help you kind of be able to do some stuff with machine learning.
All right, to get started with the code, the first thing you're going to want to do is import the NumPy library. And just so we're on the same page, I'm using a Jupyter Notebook to code this up, but you can use whatever editor you prefer. Also, all this code that I'll be going through will be on my GitHub, and the link to that will be in the description. Okay, so import NumPy as np. If that works for you, great. If it didn't work, you'll have to do a pip install. So you can go ahead into your terminal and type in pip install NumPy. And so it's already installed for me. So, and if pip doesn't work for you, try pip3 install NumPy. That should work. So the first thing that's important to know is how to initialize an array. So we'll just say that a equals np.array, and then within this, we just basically pass in a list. So 1, 2, 3. This would be a one-dimensional array containing values 1, 2, 3, as you see. And you can go ahead, if you're not using Jupyter Notebooks, and print a. Okay, cool. So we could also initialize a little bit more complex arrays. So we could do like a 2D array of floats, and I could do that the following way. We're gonna have a list within a list. So here's some float values, and then we're gonna make this 2-dimensional. So here's some more float values. And let's go ahead and print b. Cool. So now that we know how to initialize arrays, and you can keep doing this, like I can nest list within a list to create a 3-dimensional array, etc. Some other useful things to know about this is how do you get the dimension of your NumPy arrays. So if I did a dot number dimensions, so this tells me that it's 1-dimensional for a, and if I did b dot nm, it would be 2.
Shape is another important function, so get shape. If we do the first one, a.shape, this is all we have to do. It's a vector, so it's only going to tell me the one dimension because it only has one dimension, so it's size 3. If I do b.shape, it's going to tell me the rows and the columns, so this is 2 rows and 3 columns, so it should print out 2 by 3, as it does. Okay, other things, we want to know how much memory our NumPy arrays take up, so we can get the type and also get the size. So if we want to get the type, we do just a.type, a.datatype, int32 by default. So even though these are small values by default, it specifies that it should take up 4 bytes or be an int32. If we wanted to specify what type we wanted to store as, so maybe we knew that we didn't have many like big values, so we could do like an int16, and so that would take up less size, and you can see the difference in size in a sec. So right now it's int16, and if I want to see the size, there's a couple different, important functions with this. We could do a.item size, so this should tell me 2 bytes, as it does. If we left this as an int32, it will tell me 4 bytes down here, as it does. You can also do, I think, the total size. I guess a.size is the total number of elements, so the total size would be a.size times a.item size. Another way to do that is, I think, just number of bytes. As you see, that's the same thing. And you can also do this with b, so like b.item size. B's are floats, and I believe that this is an 8-byte type. So if I do b.item size, as you see, yeah, it's 8. So floats are going to be bigger than integers usually, unless you define this as like an int64. And so yeah, I usually don't even worry about the data type too much. I don't specify, but if you really want to be efficient, try to specify this so that it fits all your data. But I guess it fits all your data as tightly as possible.
All right, so now that we've gone through some of the basics, let's actually show how we access/change specific elements, rows, columns, etc. So imagine we have the array. It's going to be a 2-dimensional array, so I'm going to make this kind of long, and you'll see why in a second. Okay, so this is a 2 by 7 array. If I print that out. Okay, and I could prove that it's a 2 by 7 by doing a.shape. That's just a reminder. So what if we wanted to get a specific element? Well, to do that, we can use this notation of row, comma, column. So this is the row index, this is the column index. So I could do something just like let's say I wanted to get this 13 right here. Well, that would be in the second row, but because we start Python indexing at 0, the first row, and then the 0, 1, 2, 3, 4, 5, 5th column. So yeah, that gives us the 13 as you see down here. And one thing that's kind of cool is you can also use the negative notation, similar to lists. So I could also say the negative second element would be 13 as well, because this would be -1 and then -2. So there's a couple different ways to do this, but we'll stick with the first one. Okay, let's say we wanted to get a specific, I can't spell, row. That's pretty straightforward as well. So in this case, if we wanted the first row, we would do 0, and then because we want all columns, we use the basic slice syntax similar to lists, and I can just do a single column, and that will get me everything in the row. That's nice. What if we want a specific column? Well, if you know how to do rows, you probably know how to do columns. Let's say we wanted this row, or this column right here, 3 and 10. That would be all the rows, and then the 0, 1, 2 column. That gives me the 3, 10. And from here, we can do even some more like tricky stuff. So I'm going to just say getting a little more fancy. And we have the start index. This is just a reminder, start index, end index, and then finally the step size. So if I wanted to, let's say, get between the numbers 2 and 6, every other element, so 2, 4, and 6, well, to specify that, I would do, well, we want the first row, and then I want to start at the first element, the 2. I actually screwed that up, it should be 1. So I start at the 2, then I want to end here at the 6, which is the, it's exclusive, so that would be, I want to actually go to the 6th element, and then I want to step by 2 because I wanted 2, 4, 6, so I do 1, 6, 2. And that gives me 2, 4, 6. And I can also use the negative here and do like -2. Ah, what happened there? Oh, shoot, that was going backwards. I didn't want to change it there. I wanted to change the 6 to be -2. Ah, okay, it's exclusive, so I wanted this to actually be -1. A little bit more of a fancy way to do that. Okay, so that's how you access elements. And then if we wanted to change something, it's pretty straightforward too. Let's say I wanted to change that 13 that I originally accessed. Well, I can just do like 20. If I print out A now, that original element that was 13 is now 20. And you can do the same thing for series of numbers. So like for an entire column, let's say we want to replace this 310 column, I would do something like A colon 2 equals, let's say I wanted it to be all 5s. I could start like this. And as you see, it's all 5s, 5, 5. And then if I wanted it to be 2 different numbers, you just kind of specify the same shape as what you've subsequenced. So it'd be like 1, 2. So now you see that we have a 1, 2 in that position. Really quickly, let's just show a 3D example. If I had a 3D, so we'll say B equals NumPy array of all this. And if I print B, so if we want to get a specific element here, the recommendation I have is work outside in. So work outside in. So let's say I wanted this 4 right here. Well, the farthest outside would be which one of these do I want? And I want the first set, so I want this area right here. So if I wanted that, I would do B
0. And then now that I'm in here, I want the second row. So I want the 3, 4. So that would be 1. And now that I'm within this, I want the first, or the second element, but the first index, like that. So that gives me the 4. And you can do similar type stuff with like the colons in here. So each one of these dimensions that you're indexing, you can be all fancy with how you access elements. So I can do something like this and, you know, get 3, 4, 7, 8. And you can kind of play around with this and see how changing different things changes what you get. And if you wanted to replace in this case, basically you just have to create a subsequence that's the same dimension. So if I did B1, this, that gives me 3, 4, 7, 8. Let's say I wanted to change that to 9, 9, 8, 8. As long as it's the same dimension, it's going to work. So 9, 9, 8, 8. If I try to like do something like 9, 9, 9, 8, 8, it's going to have an error. All right, so that's the basics of indexing. I think at the end of the video, I'll do a little like challenge problem on like some advanced indexing. So look at the end of the video for that. All right, next let's go through how to initialize all sorts of different types of arrays. So to start off, let's initialize an all zeros matrix. And to do that, there's a nice built-in function called np.zeros. And we can first, I guess actually all we really need to do is specify a shape. So I did like np0 is 5. It's going to just give me a vector of 5, like 5. But I also can pass in a more complex shape. So if I wanted it to be like a 2 by 2, or 2 by 3, let's say, as you see there, I could do 3-dimensional, 2 by 3 by 3. Could even do 4-dimensional if I wanted to, 2 by 3 by 3 by 2. It gets pretty crazy, but yeah, you can do all sorts of zeros with that. Next, let's do an all ones matrix, pretty similar to the last one, np.ones of, let's say, 4 by 2 by 2. And there you go. And you can also specify the data type here. So if you wanted like all ones but in 32, you can go ahead and do that. So all ones, all zeros. However, you might want to initialize a matrix that's not ones or zeros, any other number. So for that, you can do np.full. And this one takes in 2 parameters. So the first is the shape, so 2 by 2, and then the next is the value. So if I wanted all 99s, then it's a 2 by 2 with 99. Another useful, and you can, that has data type too. So if I wanted that to be float 32, there you go. And I'll put a link in the description to a list full of these like array creation routines. Useful to know is there's also this full like. There's this full like method, and basically that just allows us to take a shape that's already built. So let's imagine we wanted to reuse that this array that we, I guess, had in the last section, A. Well, I think it's still loaded in there, just make sure. Well, I can pass in and make a array that's the same size of 4s, let's say, by doing full like. Or actually, I think I don't even have to pass in a.shape. I just have to pass in A. There we go. If I didn't use full like, I would have to do full of a.shape. I don't know if that's that useful for you, but I guess it's potentially good to know. Okay, next one. Let's say we wanted to initialize a array or a matrix of random numbers. So random decimal numbers to start. To do that, we do np.random.rand, and we specify the shape. So let's say 4 by 2. Oh, no, what did I do wrong? I'm actually confused. Tuple state. Oh. Okay, yeah, this one's a little bit different. So instead of passing in a tuple, you can pass in directly the integers you want to, the integers of the shape, so it's a kind of a weird thing to remember. So if I did the 4 by 2, in this way I would actually pass it in like that. And when you get errors like this, oftentimes you can just do a quick Google search and realize that that's what you need to do. So I can even keep going, so I can do 4 by 2 by 3, random numbers between 0 and 1. I could also pass in something like a.shape. I don't know if this would work. Let's try. Yeah, so if you wanted to pass in like a shape, you can do random sample a.shape. And that, now you see, gives us the same shape as our a from up here. So yeah, rand, and then there's random sample, which is another method. We'll keep it as rand of 4 by 2. Okay, what if you didn't want just decimal numbers, but you wanted random like integer values? Well, to do that, we can do random.rand, np.random.rand int, and in this one we're going to pass in the start value, or if you don't specify start value, it's going to just start at 0. And so if you don't specify a shape, then it's just going to do one number. So let's say we wanted a 3 by 3. What did I do wrong? And this is not shapes, actually. Size. And yeah, all the documentation has these, like, you're not expected to memorize all of these things. What I think it is helpful to see is that you see that you can do these types of things. So like when you're thinking about a problem, you can like kind of point back like, oh, I remember that that's possible. Maybe do a Google search on how to get it. But yeah, random.randin 0.7 with size 3 by 3 is here. You can also specify like a different parameter. So let's say I went 4 to 7. And I think, and if I keep running this too, it's kind of cool. You can see it changing. And so it looks like that 7 is exclusive. So if I wanted to include 7, I would stop a little bit later. You could also throw in like negative numbers here. Cool. All right. What else other than random integers? Maybe you wanted to do like the identity matrix. You can do identity of 3. This one only needs one parameter because the identity matrix, by its nature, is going to be a square matrix. What else is useful? Maybe it's useful to repeat a array a few times. So to do that, you could do, let's say we had the array 1, 2, 3. Let's say I wanted to repeat that 3 times. Pass in the array you want to repeat, and then let's print R1. See what happens. Okay. And then if I specify the axis equals 0, I don't know, I didn't do anything. What I can do is make this a 2-dimensional array. I think because it was a vector, it didn't do what I wanted to. What I want it to do is 1, 2, 3, or 1, 2, 3, 1, 2, 3, 1, 2, 3. So if I wanted to do that, now I made this a two-dimensional array, and it will repeat the inner part on the 0th axis, so we're basically making it rows. There you go. So if I make this equal to 1, that's going to be what we saw before. Cool. Okay, so next, here's a picture of an array I want you to try to initialize using everything that we kind of just went through. So all these different methods. So look at this picture and then try to put it together without just manually typing out all the numbers, because you can imagine like this isn't too big, but if you got into a matrix that was massive, you'd want to know how to build it up using these kind of like fundamental concepts. Okay, so here's the solution to that. So I can do output equals, I'm going to start with making everything ones. So ones, and it's going to be a 5 by 5 of ones. Print output. So this is what I have now. Okay, and now basically what we're going to do is fill in this middle part with zeros. So z, I'm going to just say equals np dot zeros, and that's going to be a 3 by 3. And if I print z, now we have this. Now what I can do is fill in the middle element, so that's 1 1 with a 9. And now if I print z, we get this. And then finally we need to replace the middle part of the ones matrix. So output the middle part. So that's going to be the first row to the third row. So I want the first row to the third row, and then I want the same thing with columns because it's the middle. First column to the third column, and actually this is an exclusive value, so it needs to go to 4. And that's going to equal z. And now what happens when I print output is, yay, we got what we're looking for. And actually, one thing that I think is nice is instead of using 4, I could also do -1. So basically, from the first element to the last element, do that. And as you see, it didn't change.
I thought it had to be 3 here because it's on the 4th one. This 5 here. Difference between these two is the final output. Here's 1 to final, 1 to final. I think it's this one.
This last initialization I want to go through, I guess, is a little bit different. It's over on the concept of copying, but it's something you got to be really careful about. So I'm just going to quickly mention it. I want to do exclamation points. There we go. Okay, so imagine we have 2
Points
arrays,
to the same place.
or we
in
have 1
memory.
array. Let's call it A. And so, A is just a normal array, as you can see. And let's say we want to make B a direct copy of A. So now I'm going to just do B equals A, and then print out B. And as you can see, it's still 1, 2, 3. And so I'm like, okay, I have this copy, like things are cool, it's fine. I want to change the first element in B. So I'm going to do B0 equals 100. Here's the issue. I print out B, looks good. The issue lies in if I print out A, look what happens. I just printed out A, and A now has a 100 instead of the 1, 2, 3 that I initially set it as. And that's because when we did B equals A, we just set that the variable name B points to the same thing as A does. We didn't tell like NumPy to make a copy of what is the contents of A. So that's why, because we're just pointing at the same exact thing that A is pointing, when we change the value, it also changes the value of A. So if we want to prevent that, we can use this .copy function. Oh, sorry, I shouldn't do it yet. B equals A.copy. And then when we run the cell, as you can see, 1, 2, 3, it's still there because now we're just copying the contents of what's in A. And if I print B, it has 100, 200, 100, 2, 3. Okay, so one of the big uses of NumPy is all of the math capabilities it offers. So just to kind of show some of that, one thing that it can do is element-wise, I'll just make this 4 values, element-wise addition, subtractions, element-wise, I guess, arithmetic. So
Sum of
here we
the
have
first
A,
one.
print out A, and if I want to do something like A plus 2, adds 2 to each element, you can do A minus 2, subtracts 2 from each element, A times 2, as you can see, A divided by 2, divides everything by 2. One thing to note with, and you can also do stuff like A plus equals 2, so now I printed out A in this column, it's going to be 2 plus everything. It's kind of cool. You can do like the same type of math you can do in Python. You can also create another array, np.array, and that's like, let's say, 1, 0, 1, 0. I could do something like A plus B, and that should be 2, 2, 4, 4. Oh, and because I added, if I rerun this, okay, 2, 2, 4, 4, like we expect. So all sorts of useful things. You can even do like A to the second power, 1, 4, 9, 16, and that might have made it a bigger data type, I'm not sure. Cool. We can do stuff like take the sign of all the values. So let's say we had A, we do np.sign, pass in A, gives us all the sign usually of all those values, which, you know, you have like the cosine of all those values, all sorts of useful things that you can form on an entire array or entire matrix all at once. And if you want all of the different things that you can do, I'll paste in a link here. This will all be part of the, as I mentioned before, I have this on my GitHub. So if you look in the description, you can find this exact notebook. So yeah, look up the routines right here for math, all sorts of cool stuff. All right, moving on. We're gonna still be in math, but let's jump into linear algebra type stuff. So here we are doing linear algebra. Okay, so this was kind of like basic, all sorts of functions you can do on elements. Linear algebra, so this is like really, I feel like when I'm using MATLAB, it would be doing these linear algebra type stuff. So let's say we have 2 matrices. And the big difference with linear algebra is like, we're not doing element-wise. So like, in this case, it's B. We're doing element-wise computation, so like 8 times B. In linear algebra, you're trying to multiply matrices, and that's a different process. So let's say we have 2 matrices. We'll have A, and I'm going to use the syntax we learned about earlier. I'm going to say this is a 2 by 3 matrix of all 2s. Or actually, let's make this 2 by 3 matrix of 1s. So we have A, as you can see, and then we'll have B, which is equal to np.full. It's going to be a 3 by 2, and it's going to be a value 2. So if I print out B, now we have this. And if you remember linear algebra, you have to have the columns of the first matrix be equal to the rows of the second one. So as you can see, this has 3 columns, and this has 3 rows, so we're good there. So we would multiply this row by this column, and you do the process of matrix multiplication. I'm not going to walk through the whole thing, but we should end up with a 2 by 2 matrix at the end if we want to do matrix multiplication. And it doesn't just automatically infer. If you try to do A times B, it's not going to work because these are different sizes. So what we can do is np has a matrix multiply function, and if I pass in A, then pass in B, we get 6, 6, 6, 6. Did I say enough sixes? I don't know, but yeah, it multiplies those 2 matrices. And if I try to switch up this dimension in the middle, it's not going to work because it's now incompatible. That's matrix multiplication. You can also want to do maybe some other stuff with matrices. So let's imagine I wanted to create to find the, let's say, determinant of a matrix. So we could, as a sanity check, make C equal the identity matrix. And if you are familiar with linear algebra, you know that the identity matrix has a determinant of 1. So if I do linear algebra dot determinant of C, we should get 1. 1.0 as we get. So find the determinant. There's all sorts of other good things like eigenvalues, the inverse of a matrix. So what do you multiply by a matrix to get the identity matrix? And so yeah, all sorts of good stuff on that. Like I guess I'll do. And if you want to have all this information on the other types of linear algebra stuff, here is some useful information. Definitely go to this link. And as I've said a couple times in this video, this notebook is on my GitHub page, so you can find all this there. But yeah, there's so many different things you can do with matrices and linear algebra using the NumPy library. Okay, continuing onwards, let's look at some statistics with NumPy. So kind of the easiest things we might think about when we think about, statistics. There's like min, mean, max, etc. So let's say we have this array. So let's say we want to take the min of it. You can just do np.min of stats. That's going to give us the 1 that you see there. You can do np max of stats. 6. You can also do it on like a row basis. So if I said axis equals 1, that's going to give me the min of the first row and the min of the second row. Or maybe this is a better way to see it. If I said axis equals 0, well, it's going to give me all the values that are up top here because those are all the mins. So yeah, you can do all sorts of cool stuff with mins and maxes with this. Same thing with max. Let's say axis equals 0. X equals 1, 3, and 6 is the biggest value. 3 is the biggest value, and 6 is the biggest value. You can also do np.sum of stats. If I do it just as is, it's going to sum up all the elements in the matrix, and then same thing, I can do row or column. So x equals 0 is going to add up all these terms going downwards.
I'm not sure this is the sum of all the numbers. I don't think it is.
Okay, so one of the big uses of
Watch the
video,
last part
this notebook
again.
is on my GitHub page, so you can find all of this there. But yeah, there's so many different things that you can do with matrices and linear algebra using the NumPy library. Okay, continuing onwards, let's look at some statistics, things we might think about, max, etc. So let's say we have this array. So let's say we want to take the min of it. You can just do np.min of stats. That's going to give us the 1 that you see there. You could do np max of stats, 6. You could also do it on like a row basis. So if I said axis equals 1, that's going to give me the min of the first row and the min of the second row, or maybe this is a better way to see it. If I said axis equals 0, well, it's going to give me all the values that are up top here because those are all the mins. So yeah, you can do all sorts of cool stuff with mins and maxes with this. Same thing with max. Let's say axis equals 0, axis equals 1, 3 and 6 is the biggest value. 3 is the biggest value and the 6 is the biggest value. You can also do np.sum.
So it takes the biggest value out of both.
If I do it just as is, it's going to sum up all the elements in the matrix, and then same thing, I can do row or column. So axis equals 0 is going to add up all these terms going downwards.
So it's actually 5 plus 10.
Next, let's talk a little bit about reorganizing arrays. So kind of I would say the key method within reorganizing arrays. So if I have the array, I'm going to call it before. And let's say that that is equal to this value right here. So we have before, I'll print before out. Looks like that. So let's say we wanted to, instead of this shape that it currently has, which is a 2 by 4, let's say we wanted to make it a, I don't know, a 8 by 1 or something, or maybe a 4 by 2, or a, yeah, all sorts of different things we could do. I'll start with 8 by 1. So we have before, and if we wanted to make it something else, we can do after equals before dot reshape, and then we pass in the new size we want it to have. So if we wanted it to be an 8 by 1, you can pass it in like that, and you can print out after. And as you can see, it's an 8 by 1 now. I could also say maybe I wanted it to be a 4 by 2. So now you got that. You could even pass it in as a 2 by 2 by 2. As long as it has the same amount of values, like it's fair game. So as you see, 2 by 2 by 2 still works with the reshape. What doesn't work is like if I wanted it to be a 2 by 3, the values don't fit in. So when you get errors with using the reshape, it's usually because there's a mismatch between the shape you're trying to resize it to versus the original shape. Moving onwards, let's look at vertical stacks. So vertically stacking vectors or matrices. And you know, dimensions are important in vertical stack as well. So vertical stacking matrices. Let's say we had these two arrays. If I wanted to stack, 1, 2, 3, 4 on top of 5, 6, 7, 8, I can do np.vstack, and I can pass in v1, v2. And as you see now, they're part of the same matrix, and 1, 2, 3, 4 is on top of 5, 6, 7, 8. What I can even do is keep passing these in. So let's say I wanted like 3 copies of this 5, 6, 7, 8, and only 1 copy of this, or I could interweave them. That's a vertical stack. Horizontal stacks are pretty similar, and also note here, like I can't do that. The sizes mismatch. So yep, horizontal stack, very similar. Let's say we had, we'll use some notation we've learned before. We had these two matrices. So if I printed out H1, you got like that, and then H2 is this. Well, I want H2 to be on the back of H1. I can just do an np.hstack, horizontal stack, and that will be H1 and then H2. And that did not work because I did not surround this in parentheses. Either parentheses or brackets, I think they both work. Yeah, there you go. So now we've horizontally stacked the zeros on top of or to the right of the 1. All right, let's get into some miscellaneous things. So first off, imagine you have some sort of text file with all sorts of data, and for whatever reason you choose, you don't want to use pandas, but you want to load all of that data from that file into a NumPy array.
We're skipping one
Well, we
value.
can do that without too much trouble. So I have this text file that I created, as you can see here. This is on my GitHub page. You can download it there. This is just really simple data, but it shows kind of what you can do with it, all delimited by commas, called data.txt. But what I can do is I can do np, and I can use this function called gen from text,
Is it?
and I pass in the name of the file, which is data.txt,
That should be this
and then I
one.
pass in a delimiter, which is the separator, and that's a comma. And if I do that, you see that I get that data that I just showed you. I get that. I can increase the zoom here. I get that as an array, so that's pretty nice. So I'll just call this file data equals, and file data. Yeah. One thing you notice though is it automatically cast it to a float type. And what if I wanted it to be an integer? Well, I can do another function as type, which basically copies all the data into a whatever format you specify. So I'll say int32. And as you can see, now all of this stuff is here. And if I go ahead and print file data now, it is back to what we had originally. And the reason it's back is that this actually makes a copy because the float type and the int32 type are different sizes. It can't just like in place copy everything. It doesn't really make sense to. So if I did file data equals file data dot as type int32 and then printed out file data, as you can see now it's all floats. So that's how you load data from a file. And you can change up this delimiter based on how your data is split. But I think that this gen from text will handle your new line breaks properly if that's how it's formatted. Write in the comments if you have any questions about this. Okay, the second thing I want to go through is what happened there? I didn't want that to be marked down. The second thing I want to go through with this miscellaneous section is some advanced indexing. So there's some really cool stuff you can do with NumPy. I'm going to say Boolean masking and advanced indexing. So what can we do here? So let's say I wanted to learn where in file data the value is greater than 50. So if I just type in file data greater than 50, it's pretty cool that you get false or true based on whether that specific location was greater than 50. So as you can see, there's 4 falses and then a true. If we go to our data, 4 falses and then 196 is in fact greater than 50. So that's like one way, and you can do all sorts of cool stuff with it. It's like you can do greater than or equal to, you know, all sorts of different combinations. One thing that's pretty neat is you can do file data, and then you can index based on where it is greater than 50. And by doing this, you grab only the values that actually have a value greater than 50. So that is pretty cool. And kind of the reason that this right here works is that one thing I did not mention until now is that you can index with a list in NumPy, which is pretty cool. So you have the array 1, 2, 3, 4, 5, 6, 7, 8, 9. And I wanted, let's say, the 0th spot, the 2nd spot, and then the last spot. I could do MP, or let's say that this is A. I could do A of 0, 1, or I wanted 2, 3, and 9, so I would do 1, 2, and then 8. As you see, that gives me 2, 3, and 9. I passed in a list and it indexed those spots. So basically, it also works if you like had trues and falses. It like basically if it is true, then it knows to take it. If it's false, it doesn't. So that's why this up here works. We could do all sorts of other things. So let's say I want to figure out if any value in any of these columns was greater than 50. So I can do a np.any file data greater than 50 in the axis of 0. So that should tell me, like, if we look downwards on all of these, are any of the values greater than 50? That's what happens. So false, 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 true. That's correct. True. These two values are greater than 50, even though this one isn't. False, true. Yeah, true, true, false, true. Cool. So this is telling us, yeah, what columns have a value greater than 50. And I can also do np.all. And as you see, there's less trues in this case. I think the only time that all the values are greater than 50 are right here. And yeah, you see there's 1 true in the 5th spot, which corresponds to this right here. What else can we do with this? If you did axis equals 1, it's going to be the rows. You can also do multiple conditions. So I could do like, I want file data to be greater than 50, and let's say file data is less than 100. And this syntax is very similar to Pandas here. And as I said before, NumPy builds is what's the base of Pandas, so it makes sense. No. The truth value of an array with more than one element is ambiguous. How do I do this? I think if I do something like this, it will work. Not positive. Let's see. No, I need to end it. Yeah, cool. So this is all the values that are greater than 50 but less than 100. So like the first true should happen at the 6th spot. 1, 2, 3, 4, 5, 6, as you see. And I could do something like all the spots. If I wanted to make all this not, so this means not greater than 50 and less than 100, this is going to be the reverse of what we just did. So yeah, now the 6th spot is the first false. So this meant not. So yeah, all sorts of cool stuff you can do with this Boolean masking and advanced indexing. I mean, yeah, any sort of like condition. I'll put a link and some more information about this. All right, quick little quiz on indexing. This is kind of using all sorts of advanced stuff that you just learned in that last section, and then also like some of the original stuff. So first question, basically pause the video after I ask it and then try to figure out what the command would be. So we have this matrix, and how would you index this part of the matrix? So this is the 2nd and 3rd row and the 1st and 2nd column, or 0th and 1st column, so it looks something like this. Rows, columns. Next question, how would you index this? This is something we haven't done before, but you potentially with that last section might have an idea. If not, no worries. So to do this one, you need to use 2 different lists within your indexing. So it's going to look something like this. We need the 0th, 1st, 2nd, 3rd row, and then the 1st, 2nd, 3rd, and 4th columns. That's what that is. And then final question, how would you index this? This is like also something we haven't immediately looked at, but you might be able to get, especially with that last one. Take a second. All right, that would look something like this, where you get the 0th, 4th, and 5th rows, 0, 4th, and 5th rows, and then you want columns 3 onward. So this would, like 3 onward works. You can also do like 3 to 5, You could also do 3, or like a list of 3, 4. But yeah, that's one way to do it. It's a fun little quiz. I don't know. It's, I guess, good to revisit this type of thing, like think critically about it. All right, thank you guys very much for watching. I think this is all I have for this video. Peace out.
Right. Now is the projects. I think I'm gonna stop here for now. I'm not sure if I'm gonna come back today and try to solve this, or if we'll start tomorrow. But yeah, I will see. I think I might come back today and start this today and try to finish tomorrow. But yeah, I think I'm done for now. So, see ya.